Hey, my name is Shavan Singh. I'll be presenting on behalf of Group 18. Um, what is HBC? It stands for Human Body Communication. How it works is we connect small devices to the body and we use the body as a transition channel to send signals to another device, right? Um, the two most popular types of HBC is the galvanic and capacitive model, and they use the electric field to transfer the information through the body. There is a disadvantage with this mechanism, and that is it relies on the environment. So if the environment changes, the transfer function will change. Right, so MHBC, this is the magnetic human body communication. It was proposed as a solution for the change in transfer function of the more popular types of HBC, which is the galvanic and the capacitive model. The magnetic HBC does not rely on the transfer function. So far for the MHBC, we have gotten a circuit model, right? Not much information is known about the MHBC. So far as I have read, there was a paper on which they proved that the MHBC has less path loss than the traditional methods. Right, so our project, we needed to see what effect the changes in parameter had on this MHBC model, right? For this project, the human arm was chosen as the geometry, and for the project, we wanted to see what is the effect of changing the number of transmitter coils, electrodes, what change does the body mass index and the length of the channel has on the electric and the magnetic fields. For the project, we used the COMSOL software to model the human arm, which we selected as the geometry because of time constraints. How it worked is we split up the arm into 5 different layers, right? And we got the values from other literatures as the values for the electric conductivity and so on. How it works, if you look on the right hand side, you'll see that in blue we have an electrode on one end and we apply a current. The current will produce a magnetic field. The magnetic field will travel through the arm and link the next coil. Right, so for the parameters, we varied the number of turns. We used 1 turn, 5 turn, and 7 turns. For the channel length, we used 60 centimeters and 12 centimeters, and for the BMI, we increased the amount of fat we used in the model and reduced the muscle mass by a little. And we was able to accomplish this using 5 simulations in total. With the 5 simulations, we were able to make all the relevant calculations. Right, so here we have the results from experiment 1, where we vary the number of turns, right? So the first image shows the magnetic flux density streamlines. The second one shows the magnetic flux density, and the third one shows the electric flux density. So the magnetic field and the electric field increased, the strength increased as N was increased. Also the receiver electrode emitted a stronger electric field due to Faraday's law. Basically, Faraday's law says that electric field is produced when from a magnetic field. So if N increase and the magnetic field gets stronger, that means a stronger field is hitting the receiver electrode. So the receiver electrode will emit a stronger electric field, and this could be seen from the results above over here, where we see the electric field is very weak on the left hand side, and the electric field is much stronger on the right hand side as N increase. Right, so the magnetic field and the electric field strength is not dependent on the length of the channel. So the length of the channel has no effect on the amount of field produced. However, the receiver electrode on the other side of the arm will be linked with less magnetic flux as the channel increases. So that receiver electrode will emit a weaker electric field. Right, so if you look on the right hand side to the top for the streamline plots for the magnetic field, as the channel was increased, the magnetic field rotated 90 degrees of the axis it was traveling at, and on the return path, as it was coming back to the transmitter electrode, it rotated back 90 degrees on the original path. So the magnetic field and the electric field produced was a bit more for the person with more fat, but however the density within the tissues remained the same. The ratio of the density of the person with more fat and the person with less fat, the ratio of the density was the same within the tissues. But the receiver electrode, however, produced a larger electric field for a person with less fat. These are just some results from the experiment where we increased the person's fat. Um, if you look on the right, you'll see that the arm is looking bigger because we increased the fat content by 20 cm. For the last experiment, a more accurate way to see how the change in tissues affect the fields, we could have kept the radius of the arm the same and vary the ratio between fat and muscle content. It had a few problems faced, and the two major ones was that how people were unfamiliar with the COMSOL. It was very hard to get a hang of within the amount of time we had. Um, so the MHBC looks like a very promising field. However, a lot more research needs to be put into this field given the limited amount of knowledge we know about it. That is the end of the presentation. I hope you enjoyed it.